Suri. Today I'm going to present pose constraints for consistent self-supervised monocular depth and ego motion. Let's begin by defining the problem statement. Given a camera image, which is just the projection of a scene onto the image plane, the goal is to predict the underlying 3D structure from which this image originated. This is an inverse ill-posed problem because of the loss of dimensionality during projection. But humans and other animals have evolved to be able to reconstruct 3D from the images produced by our eyes. We have special apparatus, namely stereo vision, to help us reconstruct 3D. With two eyes seeing the same object, we can geometrically calculate exactly how far the object is located by knowing the distance between our eyes. The same principle can be employed in a stereo camera setting. Here is an example of such a rectified stereo setup where the left and right images are aligned to only have a horizontal displacement between them. If we know the corresponding points in these two images, we can use triangulation to calculate the depth and reconstruct 3D. The key to this method is finding correspondences between the left and right images. For this, a neural network can be employed to estimate the deviations in pixel coordinates, also known as disparity, which is just the inverse depth. This can be used to reconstruct the right view, and a loss can be computed between the reconstructed right view and the original view. The gradients of this loss flow through the network to teach it to estimate correct depth. But not all of us have two eyes. We know that even animals and people born with a single eye are able to reconstruct 3D. How is this possible? Even with a single eye, there are multiple cues that we can rely on to able to uh, reconstruct 3D. One such important cue is motion. Here we see a static world and a moving camera. The relative motion between the camera is known as ego motion. We can use it to estimate depth. The same principle as in the stereo setup before can be generalized here. The only difference will be that instead of left and right views, we will have different frames at different timestamps. But there is a problem here. Just using inverse depth, we cannot warp and synthesize image t+1 from t. We also need the ego motion in here. Also in the stereo case, we needed ego motion, but that is just a translation and doesn't change over time there, so we didn't need it there. In this case, because we also need to predict ego motion, we employ a neural network which takes in two images and estimates the ego motion between the cameras. We use this ego motion and the predicted depth to calculate the rigid flow. That is the flow caused by ego motion assuming static world. This flow can be used to warp one image onto the other, and a loss is computed between the synthesized view and the actual one. The gradients from this loss flow through both the networks, teaching them to estimate correct depth and also the ego motion. But the problem with existing methods is that the estimated depth is not consistent over time. For the Kitty dataset, we see that the scale factor for each sequence is highly varying with respect to time. This inconsistency problem is because in the whole pipeline, the depth is estimated only from a single frame. There have been works which also estimate depth at different frames, for example here t and t+1, and enforce them to be consistent. But in this work I propose to also focus on the pose network. In particular, I propose three pose constraints for self-supervised monocular depth and ego motion. The first one is forward-backward consistency, where the pose between the t to t+1 should be the inverse of that of t+1 to t. The second is identity constraints, which states that pose from frame t to itself should be identity. Third is cyclic pose constraint, where pose from t-1 to t and t to t+1 should be same as t-1 to t+1. These constraints result in decrease in inconsistency as measured here in the first column. It also improves the overall accuracy. The reason for this accuracy improvement is having additional constraints make the solution space smaller, thereby helping the network optimize better. I also compare with other works. My method outperforms most with supervision as seen in the first half. The most interesting is the bottom half where there is no additional supervision and my method scores second best. Note that my method does not aim to replace any of these, but only to complement and can be used in conjunction with others. If this sparks your interest, please check out the full paper and stay tuned for the code. Thank you.